Okay, we're going to look at high resolution mass spectrometry. Let's just think about normal mass spec first of all. Let's say if you've got butanone. Okay, so there's butanone, and the MR of that is 72. Okay, so if you put that into a mass spec, you are going to form an ion. So knock an electron off that, and you'll have a positive ion. And so the MZ, the mass to charge ratio of that, will be equal to 72, which is the molecular weight. So if you looked at the output of the spec, you'd probably get something like 20, 40, 60, 80. Okay, so there's MZ along the bottom, the mass to charge ratio, and here's the abundance. You get something like that. You get a peak at 72. You'd also get some smaller peaks because this would fragment So you're probably going to get one like 15 for the methyl bit. That bit there all adds up to 29, so you get a peak there. And I'm just making up the abundances of these. And that other bit there, I think, is that's 43. Okay, so you get another peak there. But we're not really interested in these other peaks here. Yeah, not interested in them. We want to find out the MR of the substance. We look for the biggest peak. We're just interested in the biggest peak, sometimes called the parent ion, because all the other bits have come from that. And that gives us the MR, and we can determine the MR. The stuff we put in there, in this case, is 72. Okay, so that's at low resolution. Now, if at high resolution, imagine you had, and what I've got here is, right, imagine you had three, you had a mixture of these. You had, let's think you've got propane. The MR of that is 44. CO2, the MR of that is 44. And nitrous oxide, the MR of that is also 44. So normal mass spec, you wouldn't be able to distinguish between these three things because they've all got an MR of 44. But if you look at a very high resolution, you'd find that they don't have an MR of exactly 44. Right, if I just look, I think I've prepared it down here. I'll show you what the real, and I'll drag it up. Okay, so, right, if you look at the real MRs of those very accurately to several decimal places we've got there, you can see they're not all exactly the same. They're all slightly different. Carbon dioxide is a little bit lighter than N2O, which again itself is a bit lighter than C3H8. And let's see so you would, if you looked at the MR of those very accurately, you would be able to tell which molecule you had, because the pair, you can identify the MR of the thing. Right, let's have a look at the reason for that. Well, let's look at carbon-12. The carbon-12 isotope that they've got there, we've got carbon-16. So these aren't average molecular masses where you take into account isotopes. This is the mass of that isotope only. The oxygen 16, nitrogen 14, hydrogen 1. Right, the carbon-12 is exactly 12. That is by definition. And everything else is compared to that. So that we say carbon-12 weighs 12 units, and everything is compared to that. Well, if you look at let's look at hydrogen in particular. Hydrogen is, it should be exactly 1, but it's not. It's actually quite a lot heavier than 1. It's a good deal heavier than 1. And that's because the proton, the mass of a proton, the mass of a neutron is not the same in every nucleus, because what happens is when you have protons and neutrons in a nucleus, they're bound together by the strong nuclear force, which you don't need to worry about, but some of their mass is converted into energy. You know, Einstein's famous equation, E is equal to mc squared. Okay, so depending on which nucleus, where E is the energy, sorry, m is the mass, and c is the speed of light. So energy and mass are equivalent. So if you look at hydrogens, yeah, that is quite a lot heavier than the proton and hydrogen is quite a lot heavier. And in a star, you're probably aware that what happens is you get 4 hydrogens and they get converted into helium. And in the process of that, you get vast amounts of energy out. It's called nuclear fusion. You get loads of energy. And the reason for that is, if you look at the mass of the 4 hydrogens, this is heavier than the mass when it becomes helium. And that excess mass is turned into energy. Anyway, so much for the physics side of it. All we really need to worry about is that these isotopes, they're not, you know, oxygen is not exactly 16, the mass of oxygen there. It's a little bit lighter. Nitrogen is a tiny bit heavier than you'd expect, a tiny bit. And hydrogen, 1H, is quite considerably heavier than you'd expect it to be. So with the propane, yeah, you do, if you want to work out the MR of propane, which is 43.9, sorry, the propane is down there, 44.06, whatever. You do 4 times 12 plus 8 times that value for 1H. Carbon dioxide, which is lighter than the other two, carbon dioxide, look, is less than 44. You do 4 times 12 plus 2 times 15.99. There's no hydrogen in carbon dioxide, which is, you know, hydrogen's a bit heavier than it should be, and that's why carbon dioxide is a little bit less than 44. I think propane is the heaviest one of the lot because it's got 8 hydrogens, and the hydrogens tend to be, you know, disproportionately heavier. Right, so that is all you've got to do with high resolution mass spectroscopy. Let's have a look at another example which can be used. I've got here, right, I've got 2 compounds here. This one you will have heard of, definitely. This is glucose. And this one here is aspirin. Okay, aspirin's got this structure. So you've got a benzene ring, and it's got ethyl ethanoyl group there, and you've got a carboxylic acid group up there. Okay. Glucose, you're probably familiar with the shape with the structure of glucose. But nominally, if you add up their low resolution, they've both got an MR of 180. But if you look at it accurately, you can see the glucose is, they're slightly different values, aren't they? And the glucose is a bit on the heavier side. And again, the reason for that is because it's got quite a lot of hydrogen in there. The hydrogen is disproportionately heavier. Yeah, it has got more oxygens, and they're a bit on the light side, aren't they? Oxygen 16 is actually 15.99, but obviously having all those hydrogens makes it a little bit heavier than the aspirin. So that's all there is to high resolution mass spectroscopy. Then you've got 2 things which have the same MR nominally, but when you look at it very accurately, the MRs are slightly different because of these isotopic masses are not exactly what you'd expect them to be.